Welcome back, scholars. Today we're going to look at the last of our segment theorems. Specifically, we're going to look at the relationship between segments formed by two tangents. Let's get started. First, let's recap our definition of tangents and some of the key characteristics of tangents. We know that a tangent to a circle is any line, segment, or ray that intersects a circle in exactly one point. That point of intersection is referred to as the point of tangency. So in this figure, we have a tangent, line M, whose point of tangency is x. We also have a radius shown. That is the shortest segment drawn from the center of the circle to the point on the circle itself. This radius, drawn between the center and the point of tangency, will make a right angle with the tangent line. So in summary, a tangent to a circle is perpendicular to, that means forming a right angle, 90 degrees, the circle's radius at that point of tangency. Let's apply the definition of tangents in a few examples. In this first example, we're looking for the value of angle x, which is the vertex where these two tangents, line M and line N, meet. We know that points B and C are points of tangency, and by the definition of tangents, we know that the radius and tangent lines must meet at a right angle. I've labeled those here. We are also given the central angle, 135 degrees. Last, let's focus not on the lines and segments, but instead at this quadrilateral formed, this four-sided polygon. We know that the sum of the interior angles in a quadrilateral will be 360 degrees. So we have 90 plus 135 plus 90. That's 315 degrees between these three angles. That means that the fourth angle, x, will have to complete the 360 degrees. So 360 minus 315 equals 45 degrees. That means x is a 45-degree angle. Let's look at a second example. This time we're looking for these unknown segments x, which happen to be congruent. In the case of this top tangent, segment ST, we see that segment RS intersects at the point of tangency. So this must be a right angle, and x must be the radius of this circle. Zooming out, we can see that we have a right triangle with a base of 24, a height of x, and a hypotenuse of x plus 18. To solve for x, we'll use the Pythagorean theorem. We'll have x squared plus 24 squared equals x plus 18 quantity squared. Expanding this out, we have x squared plus 576 equals the binomial x plus 18 times x plus 18. Expanding the right-hand side out, I have x squared plus 576 equals x squared plus 36x plus 324. After subtracting x squared from both sides of the equation and 324 from both sides of the equation, I have 252 equals 36x. Dividing both sides of the equation by 36, I get x equals 7. So the radius of this circle, circle R, is 7. All right, we have one more case to consider when it comes to tangents, and that is how the segments of two tangents relate to one another. In this example, we have tangents AB and AD. They meet at a common endpoint A outside of the circle. We would like to know how AD and AB relate to one another. Let's fill in some additional information on the figure. We know that the angle between each radius and each point of tangency will be 90 degrees. Next, I'm going to draw a segment AC. In doing so, I created two right triangles. These triangles have a congruent leg, the radius, and a congruent hypotenuse. That means that they are congruent triangles by the hypotenuse leg theorem. Since corresponding parts of congruent triangles are congruent, segments AD and AB are congruent as well. To summarize, if two segments meeting at a common endpoint outside the circle are tangent to the circle, then those segments are congruent to one another. That wraps up our discussion of tangents and concludes our series on segment theorems. Thanks for watching.